Welcome to the next series in this matrix of time. This is called the quantum eraser. It's a continuation from the previous video on quantum theory. If you're just joining this and you happen to start at the quantum eraser, it's probably a good idea to go back to the previous video because the next couple of videos tie together the concepts related around quantum theory. But just as a quick summary, that on the quantum level, atomic particles behave as if they have split personality. The split personality is one where if you're not watching them, they behave as a wave. And so their attributes are distributed. And so it's as if their attributes are distributed right through the whole experiment at the same time. And if you immediately try to observe what's going on in the experiment, then the atomic particles behave as a particle. And immediately on the detector, a completely different measurement is made. So you go between not watching and seeing the detector with the green line on the left, which is an interferogram. And on the right side, if you watch, the right side is two distributions of particle going through a slit. So the question then is, if atomic particles behave differently, whether we're trying to observe them or not, the question then becomes, who is watching whom? So we can imagine that in the first instance, it's us looking at the atomic particle. That's typically how our reference frame as humans come. We typically come from our reference frame looking outside at the world. And we say that maybe it's us changing how the atomic world behaves. The other perception is that it could be the atomic particles that are observing us, and obviously how we set up the experiment changes how they behave. If we do the experiment in one format, they manifest one attribute. If we set the experiment up in a different way, they manifest a different attribute. So could it be that we're both observing each other? And, what are the implications to that? And this particular topic has brought up the concept of what is the nature of quantum reality. And that's another crisis within physics that has been going on now for, almost 100 years. I mean, it was back in the 1920s and 30s that the founders were struggling with this concept of what does quantum mechanics theory mean to what's happening at the fundamental layer of matter. And that still hasn't been resolved, and we'll go through multiple interpretations of what it could mean to quantum reality later in this series. But to resolve this who's watching who, we got an idea. Let's try this out. So what we're going to do is we're going to not observe the atomic particles until the very last piece of time before it hits the detector. And at that point, we're going to turn on our observation, turn on our equipment that can tell us where the position of the particle is and find out what happens. So what we expect is that we're not observing the particle, the atomic particle, and so it manifests in a wave format, and it's already gone through the slits. It's already created two wave patterns, and these two wave patterns are traveling in time towards the detector. So if we try and intercept at the last possible slice of time before it hits this detector, we're not going to change anything. These two waves have been traveling in time from the far side of the two slits, and they're going to hit the detector, and they're going to give us the top result, which is the green wave interference pattern, and not the particle result, which is below. So now we run the experiment, and what are the results? We find that our detector shows the particle form, not the interference form. And now we are confused. Because how is this possible? The photon wave already went through the particle, went through the slits, generated these two waves, and at the last possible second, we observed, we wanted to do an observation, and right before it hit the detector, it changed from the wave interference pattern to the particle distribution. That means in order for it to do that, it would have had to go backwards in time, change from wave to particle, go through the slits, and then behave as a particle would going through the slits. So what that does is it changes our understanding of time. What is happening here? How is it possible that this can happen? This doesn't follow the regular process of entropy like we discussed in a previous series, where we say that time is going forward because entropy goes from order to disorder and it doesn't go backwards and recreate itself. But here we have a circumstance where the sequence of cause and effect, right? So we showed the example of a mirror breaking. The cause was something hit the mirror and the effect was the mirror broke. Something dislodged an egg from a table and it hit the floor and it broke. So cause and effect pretty clearly. Here, the whole idea of sequence of cause and effect is shattered because at the last possible second, it changed from being a wave to a particle. And to do that, it had to go back in time and recreate the sequence to which it got here. And there's a term for this called retrocausality. And so you can see that this quantum eraser effect has a severe impact on the way that we consider the now or future events. An event in the now or future affects the way that matter behaves in the past. So we have a link where we're going, the arrow no longer goes forward, but now it can actually go backwards and then go forwards again in a period of time that's not possible to our concept as the way that we understand time. Now you might say, okay, well, maybe it's the effect is that this experiment is too small and everything is being done in very small increments of time. So let's change this experiment and let's make it so that there's plenty of time between the time that the particle is in the wave state and the last minute when we want to go and change and look at it. So now we're going to try a different experiment and see what happens with the dual nature of matter. So in this case, we have a quasar that is about 10 billion light years from our detector on Earth. So that's 10 billion light years, that's 670 million miles per hour for 87.7 trillion hours. So that's a long ways away. And we know from the general theory of relativity that Einstein had proposed that large masses like a galaxy tend to bend light. So if we have, in this situation, we've got a quasar, which is one of the brightest objects in the sky. And because it's 10 billion light years away and the age of the universe is estimated to be 13.7 billion, I think it is. We could round it off to 14 billion. So it's pretty close to the beginning of the universe. And there are photons that have been traveling for 10 billion light years. They've bypassed this galaxy that's somewhere in the middle. And the galaxy, due to its large mass and gravitational field, has bent light. And on Earth, we have a lens that focuses light from these two different paths. And we put a detector. And we put a detector either at the intersection of the two lights or at some point, which we call the focus, or at some point behind the focus. So what happens? So we would assume, before we figure out what's happened, that these photons of light have been traveling for 10 billion light years. And in order for them to change, they need to go back 10 billion light years to when they were first emitted by the quasar to be able to change its properties. So what happens? We take our detector, we put it right at the focus, we look at our computer, and we see an interferogram. So it basically says that light takes both ways and it interferes with itself. Then we take the detector, we move it back, and we only look at one branch of the light path, and immediately it changes to what it would be as if the photon traveled as a particle. You go back and forth, and the particle, the photon, changes its attributes from wave to particle, particle to wave. And it's not possible for it to go back and change its properties at the very beginning. So the concept is that the photon is both a particle and a wave always. And it carries these attributes with it wherever it goes, and at the very last second that a measurement is made, as they say, the probability collapses that it either manifests as a wave phenomenon or as a particle phenomenon. So this experiment really continues to challenge our concept of time and the behavior of matter. We've been discussing experiments where there were two paths, and that was done just because the focus was to understand what was going on, and it didn't help if we expanded that to 10 or 100 different options at the same time. But there's really no limit to how many paths a photon or an atomic particle can take in any one of these experiments. And in the unobserved state, the atomic particle or photon will take every one of those paths at the same time. So in this experiment, if we don't observe it, what will happen is you would have wavelets for every single one of these paths, and they would all interfere together at the detector, and you would get a very fine interferogram. What that basically means is, if we go back and look at the green pattern on the detector, instead of having a couple of peaks, there would be lots of peaks. So that, you would recognize that there were multiple paths that had come through just by the structure of what showed up on the detector. In these experiments, we've isolated it so that one single photon would go through to understand how the photon can be in two places at the same time. It can take both paths at the same time. And quantum theory is a statistical-based model, so it handles lots of particles. And in the atomic world, there are lots of electrons, and in the world generally, there are lots of photons. So quantum theory cannot predict the exact behavior of a single photon or a single electron, but is very accurate at predicting the behavior of an ensemble of protons or electrons. One way to think of it is, if you look at sociology, sociologists have been able to document the attributes of a particular culture, and the attributes are made up from a large ensemble of people's behavior. So a sociologist won't be able to predict the exact behavior of a single person, but they'll be able to predict pretty accurately the behavior of an ensemble of people within that culture. So maybe that helps you think about how this works a little bit better. Before these experiments, we had a neater model of time. We basically understood that the moments of now in the present, the arrow of time goes forward into the future, and that the present is affected by events that happened in the past. So we can draw this arrow from the past through the present and on into the future. Well, these two experiments in quantum theory blow up the past and the future and sort of validate that the atomic world exists in the eternal now. Because when we do these experiments, whether we're observing them or not at specific periods, the past is recreated based on how we observe the experiment. So it seems that all possible states of the atom and of matter are present in every moment of now. It takes quite a bit to wrap your head around this. I mean, the mystics talk about there being one moment in time, which is this moment of now. And we see that the atomic world is behaving this way, but certainly the classical world that we interface on a regular basis has this arrow of going forward from the past into the present and on into the future. We as human beings, by any act of observation or any process that we can possibly involved in, don't happen to go back and change our physical past. Now that might seem a bit bizarre that the atomic particle's future and past are recreated depending on what is happening in the present. But think of it this way. Our future exists in our imagination. So the future is all in our heads as well as the heads of everybody else on the planet. An event in the present often changes how we imagine the future. Now that one's the easier one. What about the past? The past does not exist anywhere. There are buildings and photos and so on that have captured the past, but they exist in the now, in the present. There is no past for them to exist in because it's gone. Now, what if you try to recollect your past? And an example I'll give you is two siblings that grew up with the same parents in the same household. And decades later, they share their experiences. And when you listen to the two siblings recounting the past so completely differently that you would think that there were two completely different sets of parents in two completely different homes. And so what is happening is that each one of these individuals is recreating the past as they experienced it and vocalizing it in their own way. Now, certainly there can be objective and subjective terms to all of this. Certainly, like in the quantum world, there are static attributes that are objective, and there are attributes that are subjective. And how we experience things really colors how we remember the past. And so I hope this analogy helps you to understand how the future and the past can be recreated based on what's happening in the present for the atomic world. And you can see the similarity that the now moment is the only real moment in time. So one of the ways to think of this who's watching whom idea is if we go back and we look at both properties. So we have an atom that has the particle form and its distributed form highlighted by this dotted green border on its distributed form. And then we have the human, and since we're made up of the same atomic particles, we have a particle form, which is our human body, and we have this distributed form, which is the blue dotted area. And when we look at the concept of the benchtop experiment, the first quantum eraser experiment that we talked about, we basically have a situation where you can imagine that the distributed form of the atom overlaps with the distributed form of us, and that there's some communication because now a part of us is in all parts of this distributed field, a part of the atom is in all parts of its distributed field, and there can be some interaction between the two. But when we saw in this second experiment that in order to justify the second experiment, we now have to say that the atom and the observer, now the observer right now is a human, but it also, is a measuring device, its distributed form would have to encompass 10 billion light years. Well, since the universe is only 13.7 billion light years, it basically says that the distributed form of the atom and of the measuring device would have to encompass the whole universe. And while there's nothing in physics that says that this can't be true, it does have some implications, which we'll have to discuss if we say that the interface between the atomic world and our observation of it is through this distributed mechanism. Before we get into the interpretations of what this all means for an underlying quantum reality, we need to finish one more attribute of quantum mechanics theory, and that is entanglement. Entanglement. One of the other intriguing ideas to come out of quantum theory was that the spin states of twin photons are conserved. That means they have to add up to a constant value independent of the amount of space. And this was really troubling to a number of scientists, particularly Einstein, who called it spooky action at a distance. Because basically the idea was that if you had a light source, and typically like a mercury light source, which tends to generate these twin photons, they move out in opposite directions at the speed of light. So they're moving away from each other at 2 times the speed of light. Interestingly, quantum theory predicts that these two particles are forever entangled due to the fact that spin is conserved, which we won't go into, but just realize that the behavior of these two are forever entangled independent of the amount of space. And that was troubling. So in 1935, Einstein met with 2 other scientists and they came up with a challenge that this wasn't possible, that there was something wrong, because if you took this experiment and you took one of these photons and you changed its spin state from, say, up to down, then the other one automatically has to change in order for the spin state to be conserved. And there's no way that these 2 photons can communicate that their spin state has changed from one to the other, because they're moving in opposite directions at 2 times the speed of light. And that would violate the law of physics that anything travels faster than the speed of light. If these 2 photons traveled away from each other for 5 billion years, the distance between them would be 10 billion years. And if one of the spin states of, let's say, the blue photon on the left is changed from up to down, then the other photon 10 billion light years away would immediately, instantaneously have to change from spin down to spin up. So entanglement challenges our notion of what can happen at a distance, and it challenges the notion whether that an interaction cannot happen at faster than the speed of light. About 30 years after Einstein, Podolsky, and Rosen had written their paper with this EPR challenge, a physicist by the name of John Bell had been fascinated by what these scientists had put in as a challenge. And he decided to look into it deeper. And the result was that he developed a theorem for experiments just like the EPR experiment. And his theorem assumes that a local reality exists. So as you know, if it's local, it means that matter basically has a particle form. His theorem says that if this is true, then the EPR experiment must satisfy an inequality that he developed. If the experiment results violated this inequality, then reality is in fact non-local, justifying an interaction between 2 twin photons at much greater than can be justified by the speed of light. In fact, these 2 photons could be at the edge of the known universe, 13.7 billion light years apart, and this would still hold to be true. About a decade later, after John Bell had proposed his theorem, physicists verified that in fact quantum entanglement is true, and they verified it based on John Bell's mathematics. And since then, entanglement has been verified many times. So this has some real implications about the nature of our reality. And as we talked about before, that if the atom is in its wave or distributed form, could it communicate to the light source 10 billion light years away? Well, this experiment says yes, it can. And what does that mean for our reality? What is our reality based on? Takeaway messages. The reality of the quantum world is nothing like you imagined or could imagine. The strange properties of this atomic world are not like we are used to experiencing. They're quantized properties of the atomic particle, energy, spin, and so on. Retrocausality, recreating the past from actions in the present. And entanglement. There's a part of the atomic world that can interact with other atomic matter over billions of light years instantly. In the next video, I'll explore spin, a fundamental property of matter that has, not surprisingly, unique quantum behavior. I hope you join me. If you'd like to watch more of the Matrix of Time videos, please hit the subscribe button and you'll be notified of new presentations. You can also visit my webpage at www.multidimensionaltime.com, and in there you will see a reference to a book I've written that you might be interested in. Also, I have a page with technical papers. There's an intro paper, and there is a paper called Three-Dimensional Time and Consciousness in the technical section that'd be of interest to people with and without a technical background. And then the rest of the papers require an engineering or science background because they get quite technical. So again, please hit subscribe and join me in not only future videos of this Matrix of Time. There will also be other series related to space and time that I'll be doing in the future, and you'll at least be notified of those as well. Okay, thank you very much.